together, but that was long ago. Before you left the high road and took off down the low. You knew what you were doing, I didn't even have to see. If you fool me twice, girl, I think it's a shame on me. Day by day, as love goes down in flames, all that you can say is I'm the one to blame. It's all the same, just more of your little girl games. That's why I'm walking. I'm tired of you talking down to me. Baby, I'm walking away from you and me. I wanna be free. I wanna be free from you and me.
We can start. Oh, apparently we can start. Welcome back, everybody, to the second of our story sessions. Really pleased to have with me Antonio. Antonio, would you just tell everybody who you are, please?
Who I am? Okay, I teach here at the Faculty of Informatics at UZI, excuse me. I'm a professor. I teach algorithms and data structures. There's some of my students here in the audience. Systems programming, computer networking, other courses. As a professor, I also conduct some research with some PhD students and other students. I'm an engineer. I graduated from Politecnico di Milano. It's a technical school in Italy, in Milan. And been here for a long time. I spent some time in the US at the University of Colorado in Boulder, beautiful place. That's, I can go on and on and on and tell you about me. Born and raised in Milan, Italy, so I spent there most of my life, and then moved to Boulder. I was there for about 8 years, and then I moved to Lugano in 2004. So that's a little summary of my story of my life.
Cool, thank you very much. So our title of our story is System Scalability.
Right.
Yeah. What makes you the man to sit in the chair and talk about this?
Well, there should be a question upstream from that. Are you really qualified to say anything intelligent about that?
Why should we listen to you?
Yeah, why should you listen? Yeah, why should you listen to me? It's a serious question. No, the word scalability was in the title of my PhD dissertation, I believe. So yeah, so I worked on scalability of a particular type of communication system, or I would say advanced communication and software integration system. In my dissertation, it's called an event notification system. Sometimes the term used is also publish-subscribe, if you ever heard that term. So yes, I worked on a publish-subscribe system, and the idea was to have a scalable publish-subscribe system, scalable to not just your computer, maybe to local area networks, but also to wide area networks. And so the work was mostly actually focused on routing, so scalability over, say, the internet. It doesn't mean scalability of everything. It doesn't mean scalability of applications necessarily. Although publish-subscribe was actually, and still is, in my opinion, quite successful in that respect. It's an easy way to connect components and applications based on content rather than addresses. So it kind of goes around the difficulty of integrating components and applications due to configurations, because everything is sort of automatically connected by the fact that you subscribe for something, that something is publishing, and it's implicitly connected. So again, the idea was to make it scalable, make the communication system underneath scalable. So that implies solving routing problems and message matching and routing problems. That's the kind of work that I've done, not the only area of research. that I work on. I work also on software engineering, broadly construed, some specific areas in software engineering. If you're interested, I don't mean to bore anybody with all my research projects. Also recently, scalability in terms of matching. I developed an interesting matcher for subset problems with some of my students using GPUs as a scalable super parallel platform, because the problem lends itself to scalability in that sense. So these are some of the reasons why I could say a few words about scalability. I don't actually, honestly, I don't consider myself an expert in certainly not application scalability.
Yeah, I'm reasonably sure there's no one else who wants to take your place in that chair for this subject right now, so you've got the job. I think we'll let you
say something, whether it's meaningful or not, it's a different question. But.
Okay, so we're taking questions, as we were this morning. If you weren't here, if you want to go to sly.do, and the code is AB2K18, and you get questions. I see them here, and I ask them, we hope.
Go right
Very
ahead.
empty at the moment, but we've not given much work on.
Okay.
I mean, scalability is one of those words that it can mean different things to different people.
Certainly, yes.
Sometimes it's about scaling from 1 to 2 is that's 100% whatever. So yeah, you're a mathematician.
I wish.
Throw some big numbers at us. Give us an idea of sometimes when you're talking about scalabilities, what's the size of the problems you were thinking about and looking at? If that's answerable.
I'll just come up with some numbers.
That's fine. No one will know if you're telling the truth or not. You can just
So sometimes you, okay, scalability, what does that mean? You can think of, say a web application, you're going to have a web front end, and so one measure of scalability is how many requests can you take per second? What's the throughput and number of requests? If this is say a lookup system, a database, similar measures of scalability, throughput, effectively. Another one is latency, although for applications, it depends, obviously, it depends on the application, but for many applications, latency is less important than throughput. In terms of scalability, it is important for networking. Actually, for networking, both are fundamental. Some of the biggest computers are routers, big machines, big boxes, and they answer very basic questions like where should I send this packet? IP packet coming in through an interface needs to go out to one or more of maybe 30 or 100 interfaces. Which ones? And top-level routers, they make hundreds of millions, maybe even more, decisions per interface per second. So that's a lot. That means being scalable. Scalability, I don't know. Other numbers would be number of users, number of size of a database over which you can run a particular job, some analysis, some data reduction problem. Yeah, so some of the numbers are, as I said, basic at that level. And then when you start studying the architecture of the system, you can study specific elements of the system, and then you refer to the scalability of those components, and so on and so forth. As I said, again, I'm not a super expert on scalability, but definitely. Also, you said I'm a mathematician. I'm not. I wish I was a mathematician, but I teach algorithms, and people who study algorithms, they look at scalability from the viewpoint mostly of mathematicians, and so they talk about it. Big O notation. That is the fundamental element of scalability. Do you have an algorithm that is linear, or do you have an algorithm that is sublinear, maybe logarithmic, or quadratic? There are some problems for which, even though in complexity theory quadratic isn't a big deal, you just can't apply anything that is quadratic on let's say, Google-sized tables. It's just impossible. You can't do it. So in order to scale, the very first step is figure out the right algorithm. And then you optimize, then you engineer it. So the first step is algorithmic, and then systems engineer, programming, and then low-level caching. Anyway.
So when you're looking at a scalability problem, a problem domain, are there common factors you find almost regardless of the domain that need to be overcome first, or is every domain very unique in the experience of the things you've looked at?
Both. Obviously, there are general principles, and if you study computer science, yeah, we try to teach you all that. Obviously, so just to name one, but caching, fundamental. Another one is batching versus one-by-one processing. Oftentimes, some processing requires you going through hoops to maybe switch from user space to kernel space or sending a packet into the network. Well, you better amortize that one-time big cost of, say, switching to the kernel or sending a message through the network. And so you might want to do that for a whole bunch of elements that you're processing elements, tuples, whatever, requests. There are other general principles, but then after that, you need to look at the specifics of the application, specifics of the architecture too. Some architectures, as I said, I was working on a GPU-type architecture, general graphics processors, and the processing you can do on those things is very, very. It's amazing what you can do, but it's also very complex to really get all the power out of that machine. You always have memory bandwidth problems. So you gotta, it's a lot of engineering, which is what makes it a lot of fun too.
Okay, so we're getting questions coming through now. They're actually flooding through quite fast, and I'm realizing my glasses are on the chair over there, so I have no idea what the questions actually are, but there are quite a few of them I can see. And I will do my best to read them, and they may or may not be right. But one question I have seen coming through is where does security and privacy, and is that an issue in scalability? Because obviously it's all about as fast as you can, and that.
Is that an issue with scalability? In a way, certainly, because security, generally speaking, adds complexity. Things are simpler to deal with if you don't have to worry about security. But in general, I wouldn't say that. Maybe it's more a political statement than not. But yeah, security at the very basic level is relatively cheap. Take it with a grain of salt. But yeah, security is not that complex. Obviously, there are some aspects of security that are still amazingly complex. If you really want to do computation over encrypted data, apparently it's possible. There's some doubly homomorphic encryption schemes that exist. I know nothing about it myself, but they're extremely complex, algorithmically complex. So yeah, there's some aspects of security that add a significant amount of complexity, but I think complexity shouldn't be used as an excuse not to have security. That's why the answer was a little political. But yeah, no, I wouldn't say that. It's more of an issue of design and policies, actually. Policies are more fundamental to security and privacy, in my opinion, than technology.
So design brings up another question we have here is, when you're designing an architecture to be scalable, is it about getting it right first time so that it then just grows, or is it about having something that will take you to a certain place, knowing that the design is then in a position you can re-architect on top of that later on? So are you looking for the very end goal straight away, or to get you to?
Well, you're always looking for the end goal, whether you can manage to reach that the first time around, or you need to iterate and converge or scratch a couple of times and redo from scratch. I don't know. I mean, these are more sociological and organizational problems. Of course, if you're brilliant, you come up with the right solution right away. Yeah, sure. I always do that, yeah.
That's why you're in that chair?
Yeah, of course. I mean, come on. No, of course you iterate most of the time. I would imagine. Yeah. I mean, it's an engineering process, so it's a refinement process most of the time. As I said, I don't study these things as human and sociological and development processes. Other people do, and I think they would agree that it's mostly iterative and refinement process.
Do you find there are, when you're dealing with people who are not maybe as researched in this, maybe students, or doesn't really matter who they are, are there a set of common mistakes that you think get made, things that very often people do that are always a hindrance to scalability, or you know that's just not going to work, but people don't realize?
Well, maybe it depends. I guess it depends a lot on what kind of experience and, well, I guess as your question says, inexperienced people, would they make classic mistakes? I guess so. You typically don't teach basic programming at the beginning with scalability and performance in mind that much. So depending also on the language, you want things to be very forgiving. So that means typically, yeah, allocate memory if it doesn't matter. And yeah, sure, abstraction, layers and layers and layers. And then once you need to really optimize, those things do have a cost. And sometimes the cost is unbearable. It's really too much. I wouldn't say there are particular errors. I guess as you gain experience, like in life in general, but developing systems and engineering systems, there are things that you learn to look at a lot more carefully than if you didn't have that experience. So sure, architectural questions, understanding the platform, understanding the machine, where are the costs. I guess knowing, again, if you study things in theory, yeah, there's a constant here, a constant there. But yeah, once, for example, going to disk from main memory was a huge cost. Now it's still huge, but less punishing. Anyway, yeah, understanding the architecture, I think, is fundamental. There's no, okay, here's my philosophical viewpoint here. Ready? The world is complicated. So whoever tells you that it's all simple, just buy into this abstraction, you'll be fine. I can't use foul language, but BS. It's just not right. They're trying to trick you into believing that things are simple or should be simple. If something is inherently complex, you got to deal with it. So just deal with it. Don't think the complexity can be gotten away with. You can't remove it. You can't remove complexity at some level. There are things that are simple, yes. Most things that have value, they're also complex. So just being able to deal with that and accepting that you have to deal with complexity is, I would say, if there's one advice as a teacher, mostly to students of computer science or information technology, just understand that the world is complicated. There's no magic.
Cool. I mean, a big thing in software development right now is people releasing frameworks or tools or systems that supposedly make it easy, especially for writing for multiple platforms. And I think so we learn that, yes, you can get something that's easy, but there is a price to be paid elsewhere.
Yeah, and I don't mean to completely dismiss the idea of trying to simplify things. Frameworks are great. Anything that you can come up with that would really abstract and thereby make things indeed simpler, yes, by all means, use it. But it's not a panacea. It can't solve every problem that you have. So just be aware of that. Don't be naive about complexity just not being there and silver bullets. No, there's something that is a complex activity, a complex architecture, a complex problem, whether the complexity is algorithmic or systemic or otherwise human. Sometimes the complexity is in our understanding of the problems. Sometimes the complexities are because there's human beings involved in processes, whether it be development processes or management processes and so on. Just don't be naive and consider that complexity as for what it is. So that's my advice. And I would say it's also what I see as a mistake that even students make, but also more experienced people make.
I can agree with that. I think,
Okay.
I often have far more issue with people than I do with the compiler. So, often computer science is one of those areas now where the research is maybe going on in a mix between academia and obviously industry is plowing millions of dollars into research for commercial reasons. On the whole thing of scalability, what is the balance between commercial and academic, and what are the relationships like in there? I mean, is that something you're able to comment on, or if not, feel free to make it up again, we wouldn't know.
I can talk, you know, but I'm not sure it's going to make sense. No, definitely there's differences between academic research and research in industry. I'm not so sure that it's for scalability versus another quality or another goal. It's not industry cares more about scalability and academia cares more about, well, I don't know, simplicity or elegance. No. I would say that the difference is more long-term versus short-term. It's clear that the technique or a technique is beneficial, it can be monetized, it can be applied to a business, then industry is going to be there and probably spend a significant amount of resources and probably be very effective. If it's not clear, meaning it hasn't been figured out, if it's a long-term project, if it's what they call blue sky research, very forward-looking, maybe even crazy ideas, then it's the business, I shouldn't call it business, it's the role of academia to go into that. Because that's our role. You know, more long-term, maybe not even applicable. Or some academics or some researchers who are proud, they call themselves, I do useless things. No, seriously, because that's their role. They will become useful, incredibly useful. I think there was a mathematician, if I'm not mistaken, his name was Hardy, who was one of the founders of number theory. Number theory is a branch of mathematics that's got to do with, prime numbers, let's say, just to give you an idea, you know. And he was very, very, proud to be researching things that would have absolutely no applications whatsoever. And then public key cryptography came along, and his work became incredibly important. And not just public key cryptography. I mean, you know, mathematics is that kind of thing by nature. It's something where it's pure abstraction up until the time where you actually need it and benefit from it, and becomes incredibly useful for our businesses for practical reasons. So, yeah, that's where I would put the distinction. It's not really, scalability versus, is compiler research versus database research done in academia? Nah, both. Is that long-term research is done in academia, more short-term and applied research is done in industry.
Sounds like academia is a bit like startups. Let's do something and hopefully one day it'll become useful. But,
it's
sounds
way
like academia has
upstream
more
from
success.
startups, but no, sometimes that's what it is. I'm actually not very good at that myself, but I was involved in something like this when I was in Colorado, but some of my colleagues are very good at that. It depends. It depends. There's a tech transfer, there's a space in between, the tech transfer space where things come out of academic research and they transition into more business.
We have a couple of questions that have come up on on measuring scalability.
Mm-hmm.
Obviously, you might be starting to deal with things that are now, increases are so small or in comparison that, how are there general techniques for measuring scalability? Are there tools that people use and like those? Is there anything you can?
It's a broad question. It depends on exactly what scalability of what scales. What scales of scalability? There are things that are easy to measure, relatively easy to measure. There are things that are very difficult to measure precisely, obviously. On a bigger scale, things are, in aggregate, things are relatively easy to measure. Because again, you can look at, let's say you're operating a data center, or you're operating some kind of web service or a web application. Yeah, there's some basic levels of scalability, how many requests per second, If you have a database, how many transactions per second, and that kind of thing. There are things that are more difficult to figure out at the very low level. Just measuring things that are very, very small is obviously difficult. Although tools exist, there's instrumentation tools. Big companies have instrumented code everywhere. I'm not an expert myself, once again, but I talk to people in these big companies, they say Google. They instrument everything. They know how their applications perform, so they really know, they have detailed traces. It doesn't mean that having a coherent, high-level picture and pinpointing exactly what can go wrong and why things are slightly slower or really bad, or no, that's a separate problem. That's a much, much more complicated problem. Again, measuring is relatively easy. Abstracting, finding the needle in a haystack of why things don't work right after you measured, terabytes of logs is difficult. And it's application specific, and it's obviously, there's tools, there's some research. One of my students is working on that right now.
Cool. Maybe when they've finished, we'll come back and answer the question again.
Will do. You got time?
Yeah. I didn't mean they had to finish before we finish at 3:30. That does put a bit too much pressure on the 4:30. Got quite a few questions coming in. I'm going to paraphrase them all together.
Yep.
But an interesting take in, can we learn anything from system scalability and then basically apply it to human beings in organizational scalability or team scalability when it comes to a development team or something like that? There's quite a few people asking that type of question.
Very good question. The answer is definitely yes. Now, meaning yes, we can learn things from engineering or system scalability and apply to human processes. There are two things that immediately come to mind, by no means the only ones. I'm thinking of something more sophisticated, but general strategies. One is divide and conquer, just delegate. Another one is pipelining. Any good project manager knows that the more you parallelize or put things in a good pipeline and try to feed the pipeline, never stall the pipeline, move things along. Manufacturing, they know this stuff very deeply. Other specific things, I don't know. Trying to think of analogies with systems that have to do with organizations. Something like latency, what does that mean? I don't know. At that level, I think that, human factors are more important than technological factors. But I don't know. Pipelining is a good one. Caching also, don't repeat 75 different times the same efforts. Try to reuse results, which is what caching is anyway. I guess there are some things that you can learn from systems.
I guess, humans make it complicated, don't they? A transistor or a piece of software never argues about where it's going to be in the pipeline, or which job or maybe it does, or what job it's going to do.
Yeah, humans make things complicated, but not artificially complicated. Maybe things are. Okay, let's put it this way. It's bad if it's artificially complicated. Sometimes you need the complication. Again, there are some irreducible complexities, and it's just naive, I should say stupid, to ignore it and think that you can mechanize and do everything mechanically. Especially in software development, there are many things that you really can't do. Maybe you will in, a million years, but you still can't. And so, yes, there's a human factor in there. And so it's also a matter of putting people in the condition to work productively and just be happy and satisfied, which is a general philosophy in life. You should do whatever you like and be happy with it. That's my philosophy, at least. There's some human factors and some technology factors that might combine.
So picking up on you like to be happy, you think you should be happy.
Definitely.
Of the things that you've worked on, what one, and I'm sure they've all made you ecstatically happy, but if you had to pick one that made you happiest that you got to work on it, or the result of it was great, what do you think it would be, and why that one? So I've just thrown this question totally at you out of the blue. So.
I love teaching. So teaching is a fulfilling activity for me. You know, my students might have a different opinion of my but no, I love teaching. I also love research. I like to. I'm kind of a geek. I'm an engineer at heart. I wish I was smarter enough to be a mathematician, but I'm an engineer, and I actually enjoy it. But did you mean type of activities or specific topics that I worked on?
Do you think of one project you worked on and thought that
one project that I worked on?
That was great. We were happy because we discovered this, or just the process was great, or we worked.
Many. I really liked the topic of my dissertation, which I have to give credit to my advisor at that time, Alex Wolf, who really came up with the main ideas. Meaning he really was the one who proposed the problem to me. Many other things. This thing I was telling you about on GPU, a fast matching algorithm on GPUs was a lot of fun. A lot of low-level, high-level algorithmic design, low-level system optimization, craziness. It was so much fun. Also some software engineering ideas. I've been working with a series of students, 2 or 3 at least, maybe 4 years ago, around, maybe a little bit, no, even before that, 6 years ago. It was a lot of fun, technically, and also at a human level. It's wonderful to work with people in general, students, you know. They're brilliant, they're fun, it's nice to get together, enjoy it. Yeah, of course, the human relation part of it. Yeah, actually there's a few things that I would say are not, do not make me happy. I'm not sure it's the good idea to go into that right now, but
sitting on stage answering stupid questions with some guy, not one of those.
Yeah, no. It's yeah. There's in general. I'm really I feel lucky.
So we were talking just before we started about how balancing being dean of the faculty and the teaching, makes some of the research time a little harder these days. But if time was not an issue and someone said to you, here's the funding to research any problem, what would you pick?
There are some ideas that a lot of the evolutions of my, again, going back to my PhD dissertation, this idea of content-based networking is fascinating to me. Routing problems are fascinating to me, and especially content-based routing. Some software engineering is wonderful, and I also I'm kind of a geek. I like software development myself. I tend to work closely with my students. I definitely review their codes, but I also contribute myself. With this GPU project,
So favorite programming language?
Favorite programming language? Oh, God. You already hate me now. You're going to hate me even more. I'm going to lose all my credibility. I program mostly these days in C++.
Ooh, so you were in here for the compiler session where they apologized.
I heard that, yeah.
You were the spit the bag.
Or what did they say? A good subset? Who was it? They were saying a good subset, high level, the noble subset of C++. No, C++ is a monster, but you can look at it in the right way and just selected set of features and just be it's a monster because it's really sophisticated. It's a very powerful tool, like any tool of that nature. It's a sharp knife. You can hurt yourself. But yeah, if you know how to use it, it's an amazing tool. Programmed in all sorts of languages, Java. When I was doing my master's thesis, I even worked in a language called O2C, which was part of a object-oriented database at that time that I think was close to Objective-C. So I can even claim that I did some of that. Not so much, like 20,000 lines of code maybe. Program in Java. Yeah, I use Python for my algorithms class. I'm not crazy about any specific language. I always say it's like English versus Italian. You know, it's whatever you're more comfortable with. I speak two languages, you know, English and Italian. Yeah, whatever. Yeah, you know, I don't think that the language really makes a difference.
It's okay. The damage has been done.
I know. I lost all credibility.
So, Antonio, the lover of the C++ monster, thank you very much.
Thank you.
Thank you, sir.
Oh, thanks.
I believe we go for coffee now again. Is that right? Chocolate. We go for chocolate.
Beautiful.
Thank you very much, sir.
Thanks, man.